So the change between three-dimensional holons and four-dimensional holons might not seem too significant an adjustment in the abstract. Instead of a three-dimensional space that can be analyzed arbitrarily within those three dimensions, we now work with a four-dimensional hyperspace. Calculations of a surface area as they relate to energy dissipation and its effects on decoherence take on a different dynamic, much in the same way modeling heat diffusion on a plane is different from modeling it in 3D space. But mathematically, a four-dimensional space is not terribly different from a three-dimensional space. But in the world of physics, things look pretty different. The states of a system at two adjacent points in time are causally linked in a different way than adjacent points in space. So if we consider the probability distribution of a system's state, this distribution varies very differently across the time dimension than across the space dimension. And when it comes to non-locality in space, we are reasonably intuitively receptive. We can imagine that a particle can have a probability distribution that describes its location at any given moment, or that a larger object can have a non-local aspect to its state, which dissipates as more energy is exchanged with its environment. We can visualize that. We just extend the it looks kind of, when I visualize it, like a particle with a bit of a hazy cloud around it. But when we extend this non-locality in time, that image breaks down, if for no other reason than that the visualization becomes harder when you include the time axis, because the state at a particular point in time is highly dependent on its state in adjacent points. Now, if you consider that protein in a DNA molecule from McFadden and Al-Khalili's example, with no interactions, its state is a probability density, with any interaction it has leaving an imprint on its local environment. This imprint narrows down its possible states to an increasingly determined classical state. We also refer to this process as its energy diffusing into the environment. Now, at the moment of each interaction, though, the particle of interest collapses not only its state at that instant, but it reduces the possible states at adjacent points in time as well. These states are not as widely restricted as the state during an interaction, but we might think of them as narrowing of a stream. Any bit of water has to pass through the narrowest point, the actual interaction in our metaphor, and the farther away from this narrowing in the flow the stream is, the more potential variation there is to the water's position. Now, it's fairly easy to think of a particle's position as a point within a three-dimensional probability cloud of heterogeneous density. We can represent that as a matrix of probabilities representing the likelihood of encountering the particle in a particular place. If you're watching a video, you can see an example of a matrix like that. And that doesn't cause much trouble to our intuition. We're comfortable envisioning a haze of probability around a basically classical universe. But if we add a time dimension, it makes things more difficult to visualize properly because this haze suddenly becomes very path dependent. Now, suppose if we start out with a matrix with a kind of high value in a center and then decreasing clouds of likelihoods of observing away from that, suppose that there's a drift going on, and rather than a high probability at the center, we have a bimodal distribution in our matrix of possible states. Now, suppose this density distribution cloud encounters an outside force which reduces the state. So where we have a matrix with a bimodal distribution of probabilities of observing the particle, when that outside observer observes it, that may in fact have been bimodal distribution in the probability. But if that continuous history is inaccessible to us, the most reasonable assumption would usually be that the progression was never bimodal, but that the center of a single probability peak drifted towards where we actually observed it. Now, In most interpretations of quantum mechanics, this probability cloud doesn't represent merely our best guess about the system, but the actual interstitial connection between the known beginning and the end state. Without an interaction, any number of interstitial probability distributions can be reasonably imagined. Our typical visualization of these systems involves zero-dimensional particles with three-dimensional probability clouds interacting in unquantified and infinitely divisible time. We think instead about those chains of events, we have to visualize a one-dimensional progression whose probability densities can swing very widely depending on previous states. And behavior can also be strongly impacted by what sort of energy diffusion leaves a partial impression on the local heat environment. In any actual chain of events, the progression between events will be partially constrained by the impression left on the heat environment. But multiple, though presumably countable possibilities would still take place between events. This is what a holon in time is. It's the undetermined stretch of non-locality between knowable events. So from the perspective of an outside observer, that kind of temporal holon isn't that difficult to imagine. But recall that example of a proton in a DNA chain. A proton could be in superposition of states that had and had not interacted with a neighboring particle. And it's a simple matter to imagine a proton beginning in one position, going through an ambiguous period of transit, and interacting with a helicase in a particular position different from the one where it started. So once we're comfortable with a dynamic like the quantum Zeno effect, we can accept this period of transition to be necessarily ambiguous. We might think of the energy dissipation of the particle like a proton, preventing it from having sufficient energy to change states. As a result, the transition has to be unobserved to connect the first and last states. But how does that period of ambiguity look from the perspective of the proton in transit? Now, presumably multiple possibilities would appear open to it, and the standard linear combination of states would apply, reference 15. Now, a proton is likely simple enough that it would have no memory of taking a particular path through the transition period, aside from the momentum at the moment it impacts the helicase. So the path it took between its initial and final states would be unknowable from the perspective of the helicase. But suppose now that we replace the proton in the original example with a human or a similar agent, and we zoom out far enough that only the vaguest details, like initial and final positions in spacetime, are knowable from the perspective of our observer. So we would regard the temporal coordinates, the initial and final observation, as fixed, but the relaxation time, so the period during which the agent is in motion, interacting only with its heat environment, is not available for event formation as seen from the standpoint of the observer in question, reference 12. So, unlike a proton, a human-like agent would form memories of the transition time. But like all other aspects of superposition extended through time, they'll be relatively fluid. So eyewitness testimony, for example, is weighted quite lightly in court proceedings, precisely because it doesn't really nail down observed events, and it's rather changeable and context dependent, reference 16. So when the scale between agents is sufficiently massive, the meaning of full effects the smaller agent can have on the larger one become increasingly rare. And that goes hand in hand with the smaller agent being better described as a wave than as a particle. However, entanglement in space and entanglement in time work differently as we zoom out. So in space, classical mechanics seems to appear naturally through a law of averages as scale gets increasingly large. In time, progressions are highly dependent on possible past states. So suppose a past state is not classically knowable. The longer an intervening holon of time lasts, the more different the boundary states can be, the more unpredictable the event progression is, and the more unpredictable the events they have. So unlike holons in space, which become more predictable as the scale increases, holons in time become more chaotic as they scale up. So from completely static at sub-zero time scales to truly unpredictable at longer scales. Now, classical ideas around causality are insufficient to explain the interplay between observation at different times and the the transitory holons which connect them. So as the quantum eraser experiment shows, an interaction can restrict the possible states described by a quantum wave prior to the interaction taking place. However, a quantum wave function evolving in a particular way also affects the set of future interactions which are possible. So agents at different points in time can interact bidirectionally rather than unidirectionally as we tend to imagine. Now, that is confusing to try and model, as modeling how a complex system will evolve within even a few time steps becomes increasingly difficult with the complexity of the system. So if we want to allow for a given interaction to affect the possible past as well as the possible future, it significantly increases the difficulty of understanding the dynamics. And that's one of the reasons why the idea of holonic temporality can be so powerful. If we model a holon, it doesn't really require considering actions outside itself. And it also doesn't require the effects of past causes or future attractors. A holon in time has a consistent logic that it's taken as a whole. And that doesn't require the modeling of interactions at different points in time. So for modeling purposes, it occupies only a single continuum in time which cannot be subdivided without a loss of data. Past and future aren't meaningful concepts inside a holon extended through time. That allows us a middle step in our conceptualization. So between a naive understanding of interaction of past-future and the conditionally bidirectional temporality we seem to inhabit, there lies a way of modeling via simultaneity. And simultaneity, as the term is used here, doesn't necessarily mean events occurring at identical instances in time. What it refers to is a process that cannot be subdivided along the time dimension without losing data. So two particles can become entangled before being separated, and they can remain a single holon despite existing at separated points in space. And in the same manner, a process can become entangled and remain a single holon despite existing at different points in time. So while the unobserved time needed to overcome the quantum Zeno effect is probably the most literal example of that kind of a holon, there's a very abstract example, which is that of a narrative. So although a narrative can be subdivided, some meaning is lost if the subcomponents are analyzed in isolation. What do we mean by this? Consider Chekhov's gun, reference 17. So Chekhov's gun states that a gun that's on the wall in the first act of a play must be fired before the end of the third. The gun is seen, it makes a promise to the viewer, and that promise must be kept by the end of the play. So what's the meaning of the gun in the first act? Well, the answer is very different if we're analyzing the first act as separate from the third act. Chekhov's gun is a holon. If it's analyzed only in the first act, it lacks a payoff. If it's analyzed only in the third act, it lacks foreshadowing. So like entangled particles at different positions, there are logical divisions between the gun's interactions with the narrative, but treating the different appearances as isolated reduces the information that we can draw from them. So the obvious question then is, what changes when we take into account the information a larger holon brings? One effect of the larger holon in the case of a narrative is that the meaning that is drawn. If we subdivide a play into 3 acts, the meaning of each act, analyzed individually, will be very different from the meaning drawn by the play as a whole. Now, meaning is an elusive concept, and it may be purely subjective. One interpretation of this fact would be that it has no impact on the physical world. But consider it's precisely meaning in the context of continuous time that we weigh when making decisions. Reference 18. So if we add information, although it tends to make decisions more difficult, it also tends to make them better. Again, that's a subjective measure, but it's an important one. Another question centers on how accessible the information is, which requires how accessible the information which requires dealing with holons is during the span of time bounding the holon. So it seems intuitive that an agent inside a holon has the option to interact with the other parts of the holon in such a way as to cause a collapse of the wave function, at least from its own perspective. If we return to the example of a proton in a DNA chain, the proton has no internal memory. So while it might have several interactions from its perspective, an outside observer would only observe that interaction if it changes the behavior of the molecule, which is why McFadden and Al-Khalili predict that changing the molecule in a better way, or changing the behavior of the cell in a better way, is more likely to be observed. So if an agent is a human engaged in an activity, then the memory the human builds of the events would be expected to cause a collapse of the probability space eventually. So humans are constantly orienting ourselves in time. Our amazingly big neurocortexes allow us to do that. And part of the effect this has is to limit the length of time that could be understood as a holon. So the limit in meaning that can be derived from it is also affected by this. So this may be one reason why narrative and storytelling is such a fundamental mode of our human cognition. It allows us to extend our sense of causality explicitly beyond what is possible implicitly. So it lets us draw our relationships and meaning by drawing back from a series of events that might seem disconnected and meaningless while they were being experienced. And there's an additional means which humans have for interacting with a holon extending unusually far in time. Now, flow state is a mysterious process, and there's significant controversy, and much of the available data comes from subjective reports. But one of the few hard pieces of data that we have about flow states is that it's characterized by a reduction of activity in the frontal and medial temporal lobes of the brain. So that's called transient hypofrontality, reference 19. And that isn't super surprising to anyone who recalls an experience of flow, so time dilation. If you've ever been in a car crash, you've probably experienced time slowing down, or time compression, as often happens during artistic endeavor. Those are both common characteristics of flow states. It's counterintuitive, though, when we consider the feats performed in flow states. So why should our ability to orient ourselves in time be suppressed during times of flow? People in flow often make and act on extremely precise predictions. So stories are very common of star performers skating where the puck is going to be, reference 20, or anticipating their opponent's moves, 21. So why should this become easier with a suppressed ability to orient in time? So with a traditional model of time, which is homogeneous and infinitely divisible, we would expect it wouldn't. We just wouldn't expect there to be any benefit to not orienting in time. The ability to imagine other times and reason how conditions of one will affect another should be key to making precise predictions and setting ourselves up for future success. So doing any of these things should be harder if we're unable to orient ourselves in time. The holonic model of time, though, there is a benefit of transient hyperfrontality that, or a holonic model would predict there to be a benefit of transient hyperfrontality. Specifically, if our frontal cortex typically works out how different moments relate to one another, it could be responsible for interactions between them, and therefore a collapse of the wave function, which reduces the possible outcomes. So that's in terms of practical predictions. This is one of the key pieces of this text, that flow state is characterized by an extension through time, by orienting in time less, and therefore causing less interactions between the holon of time that is being currently experienced during the flow state and other instances in time.